Okay, so today we'll continue on the more formal calculations on degenerate perturbation theory. And if you had seen the lecture notes, of course you will know that this is going to be a heavy calculation class. And okay, so but it's easy, it's very simple, it's step by step, it's just algebra. Okay, so the board is clearly visible, right?
Yes, sir.
Okay, so what we are going to do, so let us say I have a general problem with some eigenstates, and an arbitrary eigenstate in the middle of that spectrum is degenerate. Okay, and the degeneracy is like q-fold. Okay, so this picture means that if I turn on a perturbation, the perturbation is 0 here, epsilon here. If in the absence of perturbation it is degenerate, but when we turn on the perturbation it becomes it loses the degeneracy. And this is, we argued that this is generally true because you expect the degeneracy to break, like the perturbation to not impose a symmetry which is not there already, but rather break a symmetry which was there in the absence of the perturbation. This is generally true, and then you expect that the degeneracy to be lifted. It's not always true, of course, that the degeneracy will be fully lifted. It can be possible that it is partially lifted, and in that case you have to deal with that even after one order of perturbation theory. So we will also talk about that. For now, let's just assume the degeneracy is lifted. So this state has energy em0. Okay, and then what we want to do, so this is my original problem. This is q-fold. Okay, and I want to solve this problem. And I stated you last time that this is the full problem where h is h0 plus epsilon h1, such that when I go epsilon tends to 0, I fall back on some problem EL0, L0, and generally it is true that, of course, I mean generally this is always true that EL0 is EM0, but L0 is not necessarily M0. Okay. So we want to fix the M0, we want to choose M0 which is my correct M0, so some correct choice, and I will choose that on the basis on. So what is the idea, that why should I say one of these infinitely many choices is correct and the other is not? We choose it such that at any order of perturbation nothing blows up. First thing is nothing blows up, which means processes that are coming on the numerator, they should vanish to 0 whenever the denominator is 0, and we saw that as a guiding principle. And the second thing, and these operators, like this kind of operators which I like phi n en0 minus h0 is always well defined. We want to set it up such that this kind of operators are well defined. Okay, so this is basically the idea, and let's see how to proceed with that. And we stated earlier that we are going to do this by splitting the Hilbert space into two parts. One part is the degenerate part, another is the non-degenerate part, and also notice that all we are trying to find is an L0 which we want to work with, and that L0 will be always some linear combination of M0 of other L0s, and this is the coefficient that we have to find. Okay, so now the full, so let's divide the Hilbert space into two parts. One is a P0, another is a Q0, and the P0 part is basically, the Q0 is basically those states which are, there are Q such states, right? Q states, and P0 is 1 minus Q, the rest of it. Okay, and we said that just like projection operator, it satisfies the usual properties, that these are two orthogonal subspaces, so they must satisfy these properties, that P0 square, these properties will be used extensively now, that P0 Q0 is 0 and q naught square is q naught and q naught plus q naught is 1. Okay. So they must satisfy this set of properties. Okay, now let us start to number the equations because now we have to keep track of back and forth. So I will use I am going to start the numbering a little ad hoc in an ad hoc manner, which is as per in my note, like then it is easier to follow. Instead of saying the next equation 1, I'll call it equation 10. Just a origin shift. Okay. So this is my equation 10. H naught plus epsilon H1 L L L. This is my equation 10. Okay. And what I'll do, I split the problem into two parts, right? The part that is in that subspace, that is not in that subspace. So I insert this identity here and I call it, this is just an identity already there, q naught plus p naught L. And similarly, so then, okay, let me do term by term. This is so dirty. Let me use this watery one. Oops. Can you hear me? Hello? Did it get disconnected? Hello, can you hear me? It seems
Yes, sir.
Okay. So what do we get? We get H naught Q naught plus P naught L plus epsilon H1 Q naught plus P naught L Okay, so what I'll do, so I shift these two operators. And everything else is as usual. I am not changing anything else. So I call this equation as equation 12, and this is equation 11 in my note. Okay. So why can I do this? Why can I take this in this side? Can somebody show me that or argue that? No, why is it so? Why can I take this in this side? Online audience? Yes. And yeah, can you explicitly show that? What is identity? Yeah, so that is one simple way to argue that. Of course, this is identity. This is a trivial way to say that. And another way is just the way you were saying. Each of them is actually, you can show also for each of them. H naught, Q naught is 0 and H naught, P naught is 0. So write it in terms of this and show that. Okay. Okay. So now I can shift these two. So that means I can take this equation 12 and multiply P naught from left side. Okay. P naught times 12. So what happens? I get, so let me jump one step, not write everything. So P naught Q naught is 0. So if I multiply P naught here, this term will fall. there will be a P naught square term. The P naught square is P naught itself, and so on, right? I can just use the, I can do it for each term by term, and jump one step and write that. What I'll get is H naught P naught L. So everybody follow this, right? Okay. So this is one problem is that, so what I'm doing is already there in my note, but I still need to write it on board, because as you know, like I cannot leave you with something which you and expect you to read and study at home. Okay, so this is kind of redundant, this whole exercise. It's all there in the note and given in the pre-recorded form. So you can see how much energy is wasted because your unwillingness to study at home. Okay, so this term will be, yeah, this term will be P naught Q naught. So P naught Q naught is 0, and again P naught square. So the first term is, okay, I write it in this form. There is a reason for that, because H1, you cannot act P naught on this like that, right? Because H1 doesn't commute with Q naught P naught. So you have to act it on this side. So P naught H1 is Q naught P naught L. And here you will get, again, you will act Q naught on this side. Here the Q naught will act twice and give you, let me not write one step, just EL P naught L. Okay. So this is what you get by acting P naught on the left side. And similarly, if you act Q naught on 12 from the left side, you get H naught Q naught. See, what is the purpose of all this algebra? So let me take a step back and try to tell you. So the whole point is express just like before. We want to find an equation in which the left side is L and right side is everything which is not L, right? Or by not L, I mean L naughts, right? We want to express the L in terms of L naughts, right? That is the whole goal. And we have seen earlier that when we tried to do that, we ended up with a self-consistent equation where everything, so where you have L on both sides of the equation, and then we had to use series solution, right? So something similar will happen here. We have this complicated set of equation, not very complicated. I just wrote down this equation, which is the most, just expressing this equation. I inserted P naught Q naught to separate them, the sector which is degenerate and non-degenerate. And now I'm trying to write an equation where left side is L and right side is everything else other than L, which means L naught, ideally L naught, but you will also find L in this side, then you have to use the series solution, right? So this is the agenda, and that is why this equation is divided into two parts, such that I have this part where the degenerate part and non-degenerate parts are separated in this cell. Okay, so that's the whole exercise. Q naught plus P naught L. So now I have these two equations. Notice one is in the subspace that is not degenerate, another is in the subspace that is degenerate. So they are clearly separated, and separated means of course they are mixed in a weird way, and now I try to disentangle them. Okay, that is the whole game. Okay. So let's simplify it by introducing two notation. One is those states which are projected into the non-degenerate part. Also notice that so far in our exercise, we have not yet talked about what is degenerate and non-degenerate in an explicit way. We just did a division of the states into two parts. It could be any two part, but we are doing it with the agenda that eventually I want to separate the degenerate sector with the non-degenerate sector. But so far all I have done, that doesn't matter, right? Degenerate and non-degenerate, nothing matters. So I am just dividing everything into two sectors. So this is the sector which has no problem. I know in the back of my head, but right now it is just two sectors. So these are the two sectors, and I rewrite this equation 13 and 14 clearly in these two sectors. Right? So what do I get? I get H naught acting on SL. So this equation from 13 I get H naught acting on SL plus epsilon P naught H1 SL plus RL. Make sure that you understand this, okay? This material is given to you at 3 different levels, in a form of lecture note, in form of pre-recorded lecture note, pre-recorded lectures, and the live lecture, okay? So this is the last line. This is the last line. If you even don't follow this or try to follow this, then you have basically you are giving up on this whole material. So at least follow this one of these 3 things which I gave you. Okay? So try to follow it in real time, then you don't have to read that much, all these lecture notes and stuff. And the good news is just algebra, right? What else is there? So if you don't follow in here or try to follow here, then you not only have to read it, I mean you have to spend double time basically. Okay, so this is the SL part, so I should now write down the RL part. Okay, what did I do here? Yeah, this should be RL. It is written slightly wrong in my note. So this part is RL plus epsilon Q0 H1 SL plus RL EL RL. Notice I did nothing. I just relabeled things, right? This equation from here to here, I just split one equation into 2 parts. One is for the part I want, SL part. Another is the part I don't, not part I want or do not want. The part that is problematic and non-problematic, which is degenerate and non-degenerate part. And right now you don't need to worry about that because it's just 2 parts. It could have been anything. So I just divided the problem in 2 sectors and wrote down this equation in these 2 sectors and relabeled those sectors by S and R. Nothing else, right? So this is my now new equation 13 and 14. I call it 15 and 16. And what I want to clearly know what is the SL and RL. It's a pair of coupled equation, and I want to decouple them and express SL explicitly and express RL explicitly. Okay. So all I have to do, so let me just rewrite this also. So SL, so separate them in left side and right side. So SL and RL. So I get epsilon P0 H1 RL EL minus H0 minus epsilon P0 H1 P0. I just took the SL and RL and separated them in 2 sides. And epsilon Q0 H1 SL EL minus H0 minus epsilon Q0 H1 Q0. So let me call it 17 and 18. What did I do? I just separated the SL and RL into 2 sides, right? Nothing else, just rearranging things. Now all I have to do is express the RL in a form, bring them in a self-consistent form, right? So what I have to do, I have to get rid of this SL by inverting this and put them, then you will get this full RL equation, which is again the same issue where left side, right side, both RL appears in both sides. So you have to use the series solution. Right? And another thing you have to notice that how you cannot do this in an ad hoc manner, right? You have to do this in a manner that all these quantities are well defined. Right? So notice that we had this issue earlier that I want to set up my problem in a way that these terms vanish, right? These terms I want to vanish, which is basically the sandwich of H1 between the PLN, such that these first order terms don't appear. So one have to be careful that when we are inverting all these operators, so for example this operator, I can take the SL there and invert this. I can invert this with no problem because this term is not going to project anywhere in this. This is an H1 term and P0 are all the terms which are not in this sector. Right? But inverting this can be tricky. Yes.
Epsilon P0 H1 only will be there, right?
Sorry.
Epsilon P0 H1 and why there's another P0?
Where?
Another P0 won't come.
Okay. I can bring that another P naught, and the reason is P naught square is P naught. Okay, and the reason to do it in this way is just to write this H1 in a projected form. Okay, so your problem is this, that this term epsilon P naught H1 SL, for example. So this term, yeah, so I can write this as P naught H1 SL. So SL is P naught L, right? So I can write P naught H1 P naught SL. And the reason is, if I take this P naught outside, that P naught square is P naught again, right? But why do I do this? I do it in this way because I want to define this. For example, Q naught, it's useful because I want to evaluate this term separately. Okay, this is a very good point, because Q naught H1 is not a term which you can evaluate in a rounded form on its own, right? But you can do this, because now it is mi0 H1 ni0 Mn, right? It's a whole matrix on its own. Right? So this is actually a good point. This point is of these are the small subtle things which you should learn here. This is a point of aesthetics. This is not just aesthetics, also convenience. Mathematically, I don't need to do that, but this, when I do that, I can make this whole thing a standalone matrix. Right? So this EL minus H naught. So these EL and H, it is a diagonal matrix anyways. This H naught is written in this Mn basis, right? And this is also written in this basis, right? So this whole thing is a whole matrix, right? And that I can do because of bringing this P naught here. And now this whole problem, this pair of equation, let's say calculating this SL is basically the task of inverting this matrix, right? And this matrix is well defined, but this matrix is not, because just express this full form, and you will see that inverting this you will run into various problems, right? So let's just do one of them, then I'll show you the other. Okay, so let's invert this matrix 16 and 17 and try to follow through with our agenda, that I want to separate the SL and RL terms. Okay, so inverting equation 18, I have SL. So SL is basically, so notice the sequence is very important because everything is a matrix, right? You cannot just arbitrarily shuffle things here and there. So first you have to invert this in the expression of SL, equation 18. So yeah, so first you have to invert this, then you do EL minus H naught P naught H1 P naught inverse P naught H1 RL. Okay. So this is, okay, I missed the equation 19. Where is that? 16, 17. Okay, somewhere I missed numbering. Oh, okay, now I remember. 13, 14, this is 15. So this is 16, this is 17, this is 18, sorry, this is 18, this is 19. So I'm inverting 18. Okay. So inverting 18 is this, okay, epsilon P naught, and notice that we are always using the projection operator properties to do all these steps of algebra. So notice, remember these things and use that whenever you are seeing anything weird. No, sorry, P naught square is P naught, Q naught square is Q naught. Okay, we are using all this extensively. So this is my first equation, inverting this. And now I'm going to use it in the second one. So plug 20 in 19, and you will get EL minus H naught minus epsilon Q naught H1. So don't get overwhelmed by the algebra. The algebra is nothing but just moving things here and there, but keep an eye on the main agenda. So now when I replace this, when I put this, the SL comes here, and then there is a epsilon term. So epsilon squared you will get here. So you get epsilon squared Q naught H1 P naught EL minus H naught minus epsilon P naught H1 P naught inverse P naught H1 RL. So this is your equation 21. Now this is what we wanted, right? We wanted to bring it in a form. Now why did we do all this work? Why did we work so hard? So we want the equation which is only for RL. Right? We are able to successfully separate the two sectors, RL and PL. Right? So this is that equation. We similarly want a sector also for SL by doing the other way, but let's just do it in this way. Right? So we want purely an equation of RL, and in coming up to this, we have not made any approximations anywhere. Right? Now we will start to make approximation, because now we have the same situation as earlier. I have RL here and here, and then I have to use some series solution. But one good thing is that this equation is a mixed order equation already, right? Because I have epsilon here, I have epsilon square here, and then an epsilon inverse there. So this is a mixed order equation already. So even before doing a series solution is RL, I can just say that I want the order epsilon term. So 0th order. So 0th order means I am not doing any expansion in RL. So 0th order, let me call it RL0, and okay, let's not call it RL, just RL0, just to stay with the notation. So this order I want, and I want a solution of this up to order epsilon. So that will become, this term I can throw away, right? Because it's a higher order term. So I get EL0 minus EM0 minus epsilon Q naught H1 Q naught. Okay. RL. Why EM0? Because RL is nothing but this Q naught RL. So H naught acting on Q naught will only give me these eigenvalues. Right? So this is my order epsilon term. So all you have to do is solve this equation to know all the solutions and all the eigenvectors of that order. So notice this is my ED0. ED0 means the degenerate subspace. Okay, and notice another thing. This is a Q by Q matrix because it acts on this subspace, Q naught subspace. Right? So I have to diagonalize this Q by Q matrix. Basically, that's the job. So let's use a simple shorthand, and just to all this song and dance will boil down to a very cute two-term equation. So the shorthand is, I use this shorthand, that is U Q naught H1 Q naught. So this thing I called an effective matrix, effective Hamiltonian. It's a Hamiltonian of H1 projected into the subspace of this. Okay? So this terminology you will see more commonly in many other, when you take any advanced courses in atomic molecular physics, condensed matter and QFT and particle physics, that effective Hamiltonian, the concept of effective Hamiltonian you will see. Where you have some grand Hamiltonian and you want an emergent effective Hamiltonian for a low energy subspace. So this is that object, right? Which is nothing but this quantity. This is the meaning of an effective Hamiltonian. Okay? So this U is my 23. I don't call it effective Hamiltonian here yet, because effective Hamiltonian is a very interesting subject, that you can sometimes guess the form of the Hamiltonian without doing all these calculations, purely from symmetries and all that. So these are called effective Hamiltonian approaches, and almost all work is like that, right? Nobody knows the actual Hamiltonian of anything. Right? All you can do is guess a form based on various other things. Okay? But given you know that, then how can you go a lower energy subsector? This is basically one way to do that. So this is your perturbation Hamiltonian in the HD0 subspace. This is the effective Hamiltonian that is acting in that degenerate subspace. And I introduce a delta notation again, and the delta notation is nothing but, okay, I made a notation mix up. Yeah, I don't need this to be 0. This is not 0. Right? And this delta is nothing but the delta you defined earlier. It's the difference between the actual energy and the unperturbed energy. So this is, but I call it a matrix also because this is matrix. This has to be a matrix. So EL minus EM0 identity Q by Q. It's a Q by Q matrix, right? So then equation 22 can be rewritten as delta L minus epsilon U. RL 0. So your job boils down to now. So this is my equation 23 and this is my equation 24. This is my equation 25. So all this song and dance boils down to solving this equation, which is what we already got. We already discussed this intuitively when the degeneracy was in ground state. We all you have to do, at least at 0th order, is solve this equation where this epsilon, where this U is the projected perturbation Hamiltonian. That means this object into the degenerate subspace times epsilon, this energy difference that you want to calculate, minus this projected Hamiltonian, and this matrix you have to, this matrix equation you have to solve. Okay. Okay, so now the job is to diagonalize it. Okay. Everything is clear up to this, right? Online audience?
Yes, sir.
Okay, so we return to the same thing which we already knew intuitively, but why did we do all this work then? Then we will see that it's a systematic way. Now I can systematically go to higher order. So right now everything is order epsilon, then I can add the epsilon square term. All this equation will start to get complicated and we'll see how to handle that. Okay. Okay, so now my job is to solve this equation 25. So this is nothing but this equation epsilon U RL. This is 25 only, just rewritten. And two things to notice that U is of course, so this is the only formula that you actually have to remember, carry in your head to implement in real world problems, right? And where U is Q0 H1 Q0 and RL is Q0 L, which is basically expanding the piece where K0 belongs to this. The U small d, yeah, belongs to the small d subspace. Okay. So up to order epsilon, this equation looks like this. So you calculate this term, that is H111, H112, and so on. And this thing is basically, as I express this as this. So this is 1 naught L naught, just the inner product of 2 naught L naught, and so on, delta N1, 1 naught L naught, 2 naught L naught, just this inner products. Okay, this is the first correction, and solution of this will give you the energy eigenvalues, which is first order pattern, first order correction. So this, how do you solve? Just calculate the secular equation minus E minus ED0. I'm writing it as ED because it's these degenerate ones. Solve this, and remember that all you are doing, you can now go to higher order by using this form which you did earlier. But one have to be careful whenever you're introducing higher order. Remember the big O notation. If you are going to one order beyond, you have to also include this term. So it's a bit tricky. You cannot just expand here. You have to go back here and expand in this full equation. Okay. Okay. So this is the job. Now boils down to, let me say a little bit of some comments and tell you how to go to now the next order. No, there is not much to say. Yeah, so let me show you just how to go for next order. So this is my U Li0. Okay. Okay, now you have answered this question, that which set of Li0 should I use, which set of Li0 should be the one I choose out of the infinitely many combination, and this is the one which satisfies this equation. U Li0, let me call it some Ui Li0. Okay. I am removing the epsilon. The epsilon is not is just a overall factor. Okay. This is U. I should write it as capital U. Okay. This is the Li0, which is your first order, 0th order solution of those Li0s. A0. Okay. Because these Li0s will also satisfy the unperturbed equation, right? It is just that particular linear combination which is useful for the rest. Right? So now we want to go for the next term. What do we do? Now I cannot throw out the next term. So go to equation 21. And EL minus H naught. So this is now the usefulness of doing this formal solution. Now I know a systematic way to go to higher order. So this is epsilon square Q naught H1 P naught EL minus H naught minus epsilon P naught H1 P naught H1 RL. Notice I can throw away this term. Right? I can throw away this term because if I expand it, this will make me epsilon cube. Right? So I don't want that epsilon cube. I want to stay within epsilon square. So if I rearrange these terms, yes, yes. Or you can think it as a generic index also. But yeah, in this case, I'm only no. So this is actually a point. Yeah, so I am not using it strictly for degenerate subspace because all the Li0s will satisfy this, right? But out of those Li0s, we want to choose those special Li0s which satisfy this. Right? So those are my starting Li0s, lowest order. Because one of my question was, if I had this set, right? 1 0, 2 0, Q 0. Q plus 1 and so on, right? In this set, how will I find this? Which one I will choose? Now the one I will choose are the one which satisfy this. Right? So I can also use this notation, right? Everything is order 0, but the corrected ones are these. So let's say 1 tilde 0, 2 tilde 0, and Q tilde 0, and they are same, they are unchanged. There I don't do anything because they are non-degenerate. There is no problem there, right? So I can use this as a general index, but here I am only talking about this Q by Q subspace. Okay. These are those Qs. Okay. So Li0, this index is for this whole thing. But when I'm talking about this equation, then I only talking about those few Qs. Okay. It's clear, right? Okay. Okay, now all I do is the same game, that I revert this equation. Now I have this extra epsilon order term. So this is nothing but ELRL H naught plus epsilon U plus epsilon square Q naught H1 P naught EL minus H naught. You might see it is a cumbersome long equation, but just like before, there is also a physical way to remember everything. There is a physical picture. Every equation has a physical picture. Okay. Now what did I do? I just added the epsilon square term, kept only terms which are up to epsilon square, throw away everything and rearranged it such that I have this again this form. Everything is RL times some number and RL times some operator. Okay. Now notice this is like another perturbation theory problem. Why? Because I can rewrite this as a new H naught and this is a new H1. So now I have, and I know the solution of this problem already, right? So now I have a new perturbation theory problem, which is H naught plus H1. This is up to order epsilon, and this is order epsilon square, because this has this extra term. So I have to solve this new perturbation theory problem by the same protocol. So this is my equation 28. And this is my equation 29, where my H naught is, H1 is just this term, effective Hamiltonian of one higher order. Okay. And notice that I expected that after I solve this first problem, my degeneracy is removed, right? So this whole problem is now a non-degenerate perturbation theory problem. But one more catch is there, it is possible that degeneracy is not removed, right, after that. So then this again you have to play the same game, right, until the degeneracies are removed. Right? So this issue is called, sometimes the degeneracy is not removed at first order, but is removed at second order, third order, or some much higher order, right? But in general, if it is not, then I can just use the same. Now my effective problem is this, and I solve it. My first order term is, my first order correction, just the formulas we derived earlier. I not equal to J. The shift term, the transition term, Lj and Li, Kj is 0, and epsilon Ui minus E. This is basically the eigen solution of this H naught, this new H naught, right? And this eigen solution is this. Okay, so this is my equation 30, and this is 29. Okay. Okay, so let me now consolidate everything by writing down the final forms. Okay, no, before I do that, there are unfortunately couple of more complicated equations. So let me write that down. See, what did I do? So let's take a step back and look at the whole process. It's something we already discussed in the last class, so it's not a new thing, but just you might be lost in the algebra because there is a lot of algebra. So what did I do? I did the same thing which I did at the beginning, right? I wrote down the full equation with perturbation. I rearranged it in a form such that my unknown states, it's an equation for the unknown state. What is most desirable? I want expression to be in a form that I write the unknown states, which is the RL or QL or whatever the L's, in terms of the L naughts, right? The unperturbed states. And I don't get that because this equation is, I'm not solving actually, I'm just rearranging things, and that's where the answer comes. The answer is to expand this in terms of the unknown case, and that is also very reasonable answer because there has to be some expansion because it's an orthonormal set. Okay. So then once I express it, then I can solve this, bring the whole thing in a series equation and solve it term by term, order by order. Right? That gives you all the orders. So that is what I did in the non-degenerate perturbation theory. In degenerate perturbation theory, same thing we do, except now we split the problem into two parts. One part is the degenerate part, another is the non-degenerate part, and express the solutions of the. And now I want to deal with this degenerate part. And again, I play the same game and I get an equation where the degenerate part, that form appears in two sides, and I have to use the series solution. But luckily, that is already in a form that up to order epsilon, I can do the 0th order calculation without any actual expansion because it's already in this form. And I just throw away this epsilon squared term and I solve that equation. And this is not very surprising because we have seen earlier that a given order state correction is, for that you need the, for a given order energy correction, you need the state correction at one lower order. Right? So for first order energy correction, you need the, you get the R which is for one lower order. So that is what we did, and the whole exercise boils down to solving this equation, which we solve and get the first order correction in energy and 0th order. So now why I'm calling it a correction? Because you are not doing anything, you are just getting this, right? I'm calling it a correction because it is that kind of term, it is that kind of linear combination which doesn't send the higher order corrections to zero, to infinity. It doesn't blow up anything. So that is why it's a correction. Okay? Although it's the same Li0 which satisfy the same EL. Okay? Now I use the go to second order, which means I include this term, and then I end up, when I rearrange the terms, I end up reposing the problem of second order as a new perturbation problem, where the first order is this, is 0th order is this first order term, and the first order is this second order term. And if at this level, if after the first order perturbation theory, the degeneracy is removed, then it's just the problem that you have done before, it's just the non-degenerate perturbation theory problem. If not removed, then you have to go through this whole cycle again. Okay? So I hope this big picture is clear to you, and you should be able to explain it to someone else. Like that kind of clarity should be there. Right? And then you don't have to, what is there? It's just some algebra, right? That it can, once you practice it, you will never forget it. If you can explain this thing to someone. Okay. So now I know that this is now becoming a problem of non-degenerate perturbation theory, and I know how to calculate the first order correction. I just borrowed that formula which I knew already. And what do I do next? I can calculate the effective Hamiltonian, the explicit form this matrix element. Okay, do I need to do this right now, or I can just write the final form? Yeah, let me not write all the terms right now. Let me just write what is the final form you will get after you do all this. Okay, so this is the first order. So let me write the whole thing in an algorithmic form. So what do you have to do? So first, the whole task is you have to, this is your H0 plus epsilon H1. This is your full problem you want to solve, and you know this one, H0 Li0 EL Li0. Okay. So what do you do? Given this problem, you solve this problem, right? To know the correct Li0s, so this is your starting point. Let me remove this also. This is your starting point, and then you solve. So you solve this problem. So when you solve this problem, you get this first order correction in energy and 0th order correction in state. Okay, this is your first step. The second step is, so this is your second step, means you want to, this is order epsilon. So now you want to go to order epsilon square. So now you have to solve this new problem where H naught is H1 plus epsilon u. Okay, not, remember it's not that, it's a new effective Hamiltonian, and H1 is epsilon square q naught H1 P naught EL minus H naught inverse P naught H1. Okay, P naught H1, yeah. Actually, ideally, you should write with another P naught. So this is the first order. So you have to solve this thing and calculate up to first order. Again, 0th order. So 0th order state will give you second order in Li0. Okay. And no, first order in Li0 and second order in delta. Okay. So this is the next step, and so on. You can keep doing this thing for all higher order solution, and this is with the expectation that at this level your degeneracy is removed, and if it is not removed, then of course you have to again find this equation. Okay. So now let me write down the final form, that what do you expect to get after the dust settles. So this is the operational steps, and this is the blind formula that, if you can remember, that is the final form. L is L naught. So first order, what you will get is this. So remember that, okay, one more point is that why am I doing this? Because if you remember that in your first order term, you had to calculate this, right? So if you are calculating RLI, so you have to calculate this quantity, right, to get the first order correction of the at this stage, right, of this effective Hamiltonian. So how do you, so this is a tricky element, right? How do you calculate this? Okay. So this is, it's not so difficult, it's just a cumbersome expression. So let me write down it once, just such that you get a little easy about it. So I call it H1 Ij tilde, and this is nothing but, let me write with K, just to match with my note. Kj0 epsilon square H1 P naught Ed0 minus H naught inverse P0 H1 Ki0. Okay. You might be uneasy to see that this is a long expression, but it is not, because these P naughts, they are just some kind of a projection operator. So then you get epsilon square. Let me just expand them. Kj0, this term, H1 T0. So T0 is this expansion. All the states except the one which is in D subspace. Right? This is T0. Now I can calculate this quantity. This will just become a scalar. and this will go down. EG0 minus ET0. This is T0 H1 KI0. So this is summed over all the states which belongs to not in the subspace. So I call it D bar, not D. Okay. So all you have to do is express this, calculate this expression. It's a very simple. It looks cumbersome, but it's very simple. It's just those elements, those vectors Ki0, sandwiched H1 sandwiched between those subspace vectors and those which are out of the subspace. Right. That's all you have to calculate. And after you do all these calculations, let me write down the final expression. So the final expression is of this form. So now I showed you how to calculate this term, and then you get a final expression which is T0 H1 Ki0 ED0 minus ET0 T plus number T belongs to H D bar I not equal to J 0 H1 This is the order epsilon correction, and so on, order epsilon square. And you can also show, so I showed that what is the first order correction, right? The first order correction is nothing but solution of this equation. When you solve this equation, the answer you get is your delta n first order, right? Similarly, you can show the delta L second order is nothing but just what you get from perturbation theory. This will be your second order correction. So one way is you remember all this formula, or you remember this protocol. Okay. So it is not also hard to remember this formula. You just have to think in terms of what kind of processes they are. So I'm not spending time on that, but just you can remember that this is basically hopping from this subspace to the out of the subspace and then coming back to the subspace and all that. Okay. So this is basically all the formulas, and thankfully most of the problems you will do, at least for the course, you don't have to remember much of this. You rather have to remember the protocol, right? What are the set of operations that you must perform to solve a generic problem in degenerate perturbation theory. But I strongly urge you to go through this whole derivation, all the steps of the algebra, at least once, if you are continuing to do more advanced versions of this problem in various courses. Right? If this is your last course in your whole lifetime on quantum mechanics, then I would suggest that don't bother about, make sure you know how to solve problems. Okay. Okay, that's all. That's all for today. Next class I will be very easy, because next class I'll solve some problems using this idea.